This video aims to show the vision of quantum key distribution, why it's important, and how high-altitude platform-based delivery can significantly enhance the ability for regional delivery. Let's start at the beginning. What is QKD? Quantum key distribution seeks to address potential vulnerabilities in data transmission and storage. We transmit encryption key information by encoding information on single photons or weak coherent pulses to limit the amount of information an eavesdropper can gain from a communication channel without revealing themselves. The eavesdropper causes errors or loss based on how much they interact with the quantum signals, revealing themselves. The encryption is also generated using quantum randomness, meaning it is robust to attacks by quantum computers. In this section, we aim to describe individual systems and how they work together to deliver early applications. The high-altitude platform has a range of optical channels, or put simply, different lasers for different purposes. One is the beacon and synchronization signal, allowing the transmitter and optical ground station to share a common starting point for timing, which is essential for the communications. The other is the quantum signal, which can be a continuous or discrete variable protocol. The quantum transmitter module, in terms of the discrete variable protocol, is a single photon level, or actual single photon source, which is modulated in such a way that we can transmit our quantum secure key securely. A radio frequency, millimeter wave, or optical signal is used by the HAPS as a communications channel to process the quantum key, share the GPS coordinates, and share conventional communication information. There's a size, weight, and power restriction on the HAPS, and the payload must meet the requirements. The optical ground station is made of a telescope, a fast-tracking optical mount to hold the telescope and other optical systems, the conventional optical systems to measure the non-quantum signals, the quantum measurement, and a radio frequency or millimeter wave or optical system capable of measuring the conventional GPS and comms signals. The transmitter is over 15 kilometers away from the receiver. The optical beam diverges, meaning the size of the beam on the ground is greater than the telescope diameter. The transmitter combines optical signals and directs them at an optical ground station. The optical ground station then separates them to measure individually. We're now going to look at the basic principles and commonalities, as well as describing the variants when implementing QKD. This is a process to share a common key between two independent optical ground stations. 1. The HAPS, the satellite in the image, acting as a transmitter, performs QKD with an optical ground station, sharing key A. The QKD signal can be either a continuous or discrete variable protocol. 2. The same HAPS then performs QKD with a second independent optical ground station, sharing key B. 3. To enable the sharing of a common key, the HAP transmits key A exclusive or key B to the second optical ground station. 4. With the common key, the two optical ground stations can encrypt their information with quantum secure keys. We're now going to look at how unique link length range for HAPS can allow for a diverged beam to simplify a problem. The coarse pointing acquisition and tracking, or PAT subsystem, includes a gimbal with the light source and telescope mounted on it. The gimbal is able to steer according to coordinates of two sites obtained from a differential GPS system. The fine PAT subsystem includes an optical beacon, an indium gallium arsenide camera mounted on a gimbal, spatial light modulator, photo detector, and quadrant detector able to feed back the steering information to the gimbal controller and the fast steering mirror. The feedback loop compensates for vibrations and other movements. Assuming a light source with 0.1 milliradian divergence is carried by the HAP, after 20 kilometers of propagation, the beam lands on the ground with a 100 centimeter diameter footprint, compared with the 20 centimeter receiver telescope aperture. The same 0.1 milliradian light source carried by a satellite, after roughly 500 kilometers of propagation, creates a 2,500 centimeter diameter footprint. The photons the source sends land everywhere within the footprint. The smaller the footprint, the more photons the optical ground station telescope can collect, indicating a larger margin of the HAP link budget than satellite. We can exploit the larger margin available with HAPS compared with satellites to reduce difficulties of pointing and tracking. Let's take a detailed look at the different types of aerial and HAP platform. HAPS are aircraft and airships situated at an altitude of 17 to 22 kilometres. They are often quasi-stationary, capable of providing regional coverage. They are often powered by a combination of solar power and batteries. Solar power is used to power the craft and payload, with the excess stored in the batteries for use during night. Now it's on to the phased test programme. Phase 1 consists of short-range terrestrial and aerial trials. The first experiment will be a ground-to-ground QKD link with a retroreflector mounted on a steerable, stabilised platform. Experiment 2 will be an air-to-ground QKD link with the light source carried by a helikite. The 21 cubic metre helikite is able to lift 9 kilograms payload up to 400 metres altitude. In this final section, we'll be looking at future developments and application scenarios. Integrated HAPS satellite QKD delivery. To provide worldwide delivery of QKD, it would be best to use HAPS in combination with satellites. Satellites will provide potentially global reach, with HAPS providing a more cost-effective delivery direct to the end user. Increasing the efficiency of QKD. QKD is currently delivered using the protocols based on CV and DV operation. There is scope to significantly improve the efficiency of these methods, without compromising on the security. Commercial exploitation opportunities. As the quantum technology and delivery methods develop, the costs of supplying security based on QKD will reduce dramatically, enabling many more applications, including for large numbers of users, regional delivery to multiple sites, remote delivery, and maritime applications.